Yeah, sorry about that. Anyway, we're going to be talking about my first research project at my new job. But first, before we get to that, a little bit about myself. My name is David Bianco. I'm a security strategist with the Surge research team at Splunk. The nice thing about Surge is that we do basic cybersecurity research, not necessarily product-oriented or anything like that, just for basically the general good of the cybersecurity community and the rest of the industry even. And so we get paid to research and publish what we find. And this is pretty much what we're going to be talking about today. When I first joined Surge in May of 2022, I knew that I was going to have to choose my first research project at some point. Like, there was 2 or 3 months of like settling in and, you know, taking all the required corporate trainings and meeting all the people and that, but eventually it was going to come down to I need to figure out what my first research project is. And I kind of have this issue, like a lot of times I don't know what I'm going to want to work on, especially these projects that are like between 3 to 6 months projects. So they're not terribly long, but long enough that you might get sick of it in the end. So I really wanted something that was kind of cool. I knew that as a newly minted Splunk employee, I had an unlimited Splunk license, don't hate me, and I wanted to use it, but I also wanted to get something like no one had really ever looked at, ideally something that people rarely think of. So I had actually worked with a technology called certificate transparency. Anybody familiar with certificate transparency? Yes, a few people. I worked at it at my previous employer on some side projects just to check out things. Like, we'll talk about certificate transparency in a bit, but the idea of it is it's a real-time log of all of the TLS certificates that are issued more or less for all websites. And having access to that before, I had it as a data stream, so I could look at incoming new certificates as they were registered before they even went online to try to detect like brand impersonation or phishing sites and things like that. But in this case, that wasn't exactly what I had in mind. I said, well, you know, I could use this same technology, this certificate transparency technology, and I could actually legitimately look at every single secure web server on the internet. So that's pretty much what I did. What would I do if I had all that data? I kind of quickly focused on the certificates themselves. There are some interesting pieces about the certificates. If probably most of us are roughly familiar with how the certificate trust works. Like, a certificate authority issues a certificate to you, they sign it, and there's a root certificate authority somewhere involved and things like that. That whole certificate chain of trust. Well, it turns out all of our web browsers and operating systems and whatever have these built-in sets of certificate authorities that they trust. And they come from the factory like that, and you don't really have a lot of choice. I mean, you can go in and delete things if you decide that there's a specific certificate authority that you don't like, and you don't want to trust them. I'm going off camera here. But for the most part, nobody really does that often. Chrome comes with, what is it, at the time when I tested it on my own Chrome browser, 138 trusted roots. Safari and Mac OS use a shared pool, so they're like 154. Even Firefox has like 54 of these. And these numbers vary a little bit over time, so they may even be a little bit different than they are now. But the point is, each one of these browsers, they have a set of requirements that if you fulfill the requirements, you can become a trusted root certificate authority and get shipped by default. And the requirements are meant to address let's say the legitimacy of the root CA. Are they a serious organization that tries to, have best practices and comply with these best practices? Have they published their policies and procedures for peer review and things like that? But what they don't really address is, have these certificate authorities been issuing certificates that ended up being used for malicious purposes? So I decided that that might be a really good goal. Like, they're trying to attack it from the front end. Is the root CA's policies and procedures such that we think that they might be doing a good job? I'm trying to detect it from the back end. After the certificates are actually out in the wild, which ones have been used for malicious purposes? And then we could potentially rank the certificate authorities on whether they have issued more than or less than their share of certificates that ended up being used for evil. Although I was the lead on this project, I was not the only person working on it. Another nice thing about working for Surge is that we are very, very collaborative, both within our own team and with other people inside Splunk, and even, as you'll see a little bit later, folks outside of our own organization. So I just want to give a shout out to the 3 people that helped me the most on this. They were part of the project team. That's Michael Björkeland, Kelsey Bourne, and Philip Drager. Philip has excellent fashion-forward jacket style, but he is also one of our lead data scientists. Kelsey was also a data scientist directly attached to Surge, although she's no longer with Splunk. And then Michael Björkeland, who was a system engineer who had a lot of hands-on expertise deploying Splunk architectures really quickly. So it was nice to have all 3 of them advise me on this project and help me out. So in theory, to do what I was trying to do would be really simple. You kind of uh-oh, what happened to my slides?
He's going to have to reconnect to Zoom because your recording's not happening right now. So if you can keep presenting, he's just going to get the recording.
Okay, can I have my slides back? Okay. Sorry, some recording issue. Anyway, as I was saying, in theory, it should be really simple to do what I was trying to do. You download all the certificates on the internet. You
are in the meeting now.
You rank them.
Recording in progress.
Like each one of those, if you listen to that, you'll see each one of those is a project kind of in itself, right? So when I say it should be pretty simple, that is the overall approach, but it's never that simple. Some of you may not be familiar with the innards of an X509 certificate like the ones we use for websites. Don't worry, this is going to be super brief, but there's just a few pieces of key information in a typical certificate that I want to bring to your mind here. The first one is the subject, or it's the name of the website. Whose certificate is this? This is the certificate for www.splunk.com. So no one else could use this certificate unless they called themselves www.splunk.com. So that's the subject. The next thing is there's a number of certificate authorities that are usually involved. The most direct one is the issuing CA. That is the certificate authority that actually created the www.splunk.com certificate. So that's this one here. It's a DigiCert, one of several issuing CAs that DigiCert runs. And I point that out because it's not the only CA that's involved. You'll also see some other things. So down here on the bottom, we have alternate names. SAN stands for Subject Alternate Name, but it basically means, you know, you can take the same certificate and use it for other website names. So you'll often see www.something.com as well as something.com and maybe star.something.com. Like Google does this forever, you know, all the time. There will be multiple subject alternate names in a lot of these certificates, which means that when you're matching up, you not only have to match up that subject, but you also have to match up all of the alternate names as well. You may have heard this idea of the chain of trust. Take a look here at the bottom. This is the actual certificate, www.splunk.com. Here's the issuing CA. This is the certificate authority that created the certificate, or signed it anyway. But turns out there's a lot of them. There's something like 78,000 of these, and you don't actually want to ship 78,000 entry databases in all your browsers. Actually, there are a hierarchy of certificate authorities. In this case, there's a DigiCert Global Root CA, and the root CAs are what is actually shipped with your browsers. And the idea is you have a list of root CAs that you trust, and I'm sure most of you probably know about certificate verification. So the point is that we need to look at not only the issuing certificate, but certificate authority, but also the root certificate authority, because we want to take a look at both levels to see what's going on. Technically, a lot of certificates will have multiple levels of certificate authorities, not just a root and an issuer, but everyone has a root and an issuer. So we chose those two levels. And there's that root CA, sorry. Now, certificate validation, like I said, probably most of us know a little bit about this. Your web browser gets a certificate from the server. It looks at the server's name, and it says, this is supposed to be www.splunk.com. This is a certificate for www.splunk.com. If it is, then it says, okay, is it signed by a CA that I trust? No, but it's signed by an issuing CA. Well, that issuing CA has its own certificate in there. And who's that signed by? And who's that signed by? And who's that signed by? All the way up until you get to the root CA. And the root CA doesn't have an additional signature, or maybe it has its own signature. And if you're at the top of the chain, then that CA is somebody that you trust in your database, and all of the other certificates, all of the other signatures matched up, you trust it. It's not the only thing, but that's what most of us know about certificate validation. Like there are some things that they do to kind of prevent certain scenarios. So like one scenario is if the site owner experiences a break-in, or they're tricked into compromising their key, or something like that. And so the secret key for their certificate might be compromised. They can notify their issuing CA, and they'll probably add this to a certificate revocation list or some similar thing. There's an online protocol for that as well. Basically saying, even though all of the signatures matched, no longer trust this certificate because it has been compromised. And so that's also a key part of certificate validation, is checking, most commonly, the certificate revocation list. But what happens if the certificate authority loses control of their keys? This actually has happened in the past with some fairly high-profile breaches and security incidents. One of the big ones that comes to mind is in 2011, the certificate authority Komodo, they found a bunch of valid, signed, unrevoked certificates being used by threat actors in the wild. And what had happened was the threat actors were able to manipulate Komodo's backend. I don't know if they actually got access to the keys themselves, but they were actually able to manipulate the backend to cause the signature to be generated. And that they could forge their own certificates that looked valid, but really were not. So what happens, there was nothing built into the revocation or validation protocol to kind of guard against that scenario. So what happened was in about 2012, I think it was, some Google researchers came out and they said, well, what if we just publish a list of all of the certificates that our certificate authority has ever signed? That way, and not only that list will be very large, but we'll give you a very fast API that you could easily look up. And when you get a certificate and all the signatures match and it's not on a certificate revocation list, you could also additionally check really quickly with they call it the certificate transparency log. You could look at a CTL and just ask it, was this certificate actually created by a legitimate CA process? And if yes, you're good, and if no, something's wrong. There are a whole bunch of different certificate transparency logs operated by different organizations that just have like some kind of interest in making the internet run right. Like Google runs a number of them, a lot of the big root CA organizations do. There's even some other private companies that, like internet service providers or something, that have their own, there's a ton of them. So I have to give away some prizes. So while we're on the subject of certificate transparency, let's see. I have 2 prizes here, and if you can give me the correct answer, you can have your choice. First, I have a lock-picking set, some simple lock-picks from Southward, and a nice little lock-picking manual. On the other hand, I have the Blue Nomicon, which is a book that my team at Splunk published earlier this year. It's a compendium of chapters about network defense by lots of different industry recognized professionals, including, I have one in here about the origins of the Pyramid of Pain. So if you can get the answer to my trivia question, I will let you choose which of these 2 fabulous prizes. I said that the certificate transparency came out in 2012. It says on the slide that Chrome has required certificate transparency for all web browsers or all websites since 2018. But at what point, what year did Chrome start supporting CTL validation as an option? Sometime between 2012 and 2018. So there should be at least 6 of you raising your hand. Yes? Yeah, it was in 2015. Congratulations. Which one would you like? Excellent choice, sir. Okay. Yes, and so in 2015, Chrome started supporting that for, I think it was just for extended validation certificates, like the super secure ones. But in 2018, they made it a requirement for every certificate, meaning, and this is important to us and especially to my project, meaning that all of a sudden, starting in 2018, no Chrome users could access an SSL website unless their certificates were in one of the certificate transparency logs. Meaning the certificate transparency logs, starting in 2018, basically had a complete copy of all certificates for all websites. because no one wanted to be the website that Chrome users couldn't go to. Most browsers today support it. Firefox, I think, is still the biggest one that does not. I'm not sure why, but most of the other ones, the bigger ones, Safari, of course, Edge, based on Chrome, they all do. Another key thing is that these are all API-driven. They're public. You don't have to sign up for it. Anybody can query it. And there are a number of API endpoints, one of which is give me this certificate or give me this range of certificates by ID number, which will become important later. So what I did actually was I used certificate transparency logs to download all of the certificates from 2021 and 2022. There was a few other years mixed in there, just the way that the logs are, but it's primarily 2021 and 2022. I'll talk a little bit later about the challenges I faced on that, but basically once I got all those, I found that there were about a little bit over 5 billion certificates, so 5 billion secure websites. Only websites, so not anything like if you had a secure email server or anything like that, they don't really do certificate transparency. It's only web browsers and web servers. So 5 billion unique website certificates in the data set. There were about just a shade under 497 unique root certificate authorities, and 78,000 issuing CAs. I queried 15 different certificate transparency logs because basically I just chose the built-in set that Google Chrome came with, because everything was going to be in there if they wanted Chrome users to be able to look at it. So, just as a fun thing, Philip helped me with some of the large-scale visualizations here. I just visualized like the relationships between the issuing CAs and the root CAs, totally skipping over any intermediate CAs because we're only concerned with the issuers and the roots. As probably expected, most of these things, like all these little dots here basically, most of these are kind of self-contained little universes with probably one root CA and some number between 1 and a few different certificate issuing CAs attached to that root CA. But there were some bigger things. Like you can see this big thing here. This is DigiCert's ecosystem because they bought, I think it was Symantec and someone else who I'm forgetting at the moment, around 2017. So all of those certificate authorities then became cross-signed, so that and some of the issuers eventually changed from their original Symantec root CA to a DigiCert CA. So there's a little bit of structure there, but most of them look kind of like this. Maybe the number will be a little bit different, but this is right in the middle is the root CA. This particular one happens to be Deutsche Telekom. And then Deutsche Telekom as the root CA is used by a number of different issuers. It turns out most of these are German universities. Not all of them, but most of these are German universities, and they're issuing certificates for their own web servers and also probably their own students and some other things. So in this case, I want to say this carefully so I don't give you the wrong impression. The colors of these dots have to do with the relative risk of each of those CAs, like how many they've issued that turned out to be used for bad things, but only relative to their peers. So at this level, it's a lot of noise. So the colors don't really mean anything. Just these white ones doesn't mean these are objectively bad. But they just give you a little bit of confidence that they're not all the same, right? There's a little bit of variation. Zoom in on the other one. I said the other one was DigiCert. This one is actually, gosh, I'm blanking on the name, but it's the same kind of situation. They bought, it's Sectigo, sorry. This is Sectigo. They bought Komodo and a couple of other CAs around 2018, I want to say. So again, you can kind of see like they cross-signed a bunch of their root certificate authorities to make sure that they would all still function, and all of the existing issued certificates, some of which were valid for multiple years, would still continue to work. Some of the issuers during that time switched from their old, let's say, Komodo root CA to the new Sectigo's root CAs or something like that. So there's a couple of big structures in that data that almost all have to do with mergers and acquisitions. So it's kind of neat to see how the business landscape had affected the technical issuing of certificates and their certificate authorities. Now the second piece was, now we have all the data from the websites. The other thing is I needed some threat intelligence. I basically needed to know a third-party view of what was bad in my data. One of the things I mentioned earlier was that I really enjoy how Surge is very collaborative, even outside of Splunk, with other security researchers or other security teams. We actually partnered with 7 different other organizations that specialized in some kind of threat intelligence. And we were able to take in, actually, the total amount of threat intelligence we took in was about 300, and by memory, I say about 365 million indicators, mostly domains. There was like literally 5 individual marked certificates, but most of it was by domain name. From 7 different providers all over the world, because we wanted to counter any geographic bias. The largest was Domain Tools. So we actually we had a really close partnership with them. So big shout outs to all of these organizations, Domain Tools, Group IB, the Yahoo Paranoids, internal security just for Yahoo, but they have a very good threat intelligence database. FIRST, if you're not familiar, FIRST is the Forum of Incident Response and Security Teams. It's a very international organization. And one of the things that they do is they maintain their own threat intelligence platform for the use of their members. And they were nice enough to let us use it because I am a member of FIRST. And then also JP Cert CC. I can't really say this was like a partnership because they actually publish a lot of their data. So they actually have a GitHub where they publish all of the data that they've seen, primarily about phishing and spam. But we contacted them and said, hey, is it cool? And they were like, that would be great. That would be awesome. You have permission. Please use it. And so big shout outs to Domain Tools, Group IBs, Yahoo, FIRST, and JP Cert CC, because we have no threat intelligence data. We would not have been able to do this project without our intel providers. We even had a couple that declined to be named. So if you notice, there's only 5 on the slide, and I said 7. You didn't catch me in a lie. They just they did not want to be publicly revealed. So now we have 5 billion certificates and like 180 million pieces of threat intel data, mostly domains. This was like a big data set. We did have some challenges. I can't say it was super easy. The first challenge, of course, was just getting all of that data. Actually getting the threat intelligence data was not too bad. I just called up some people, and if they agreed, we ended up like sending They sent me CSVs or gave me API access or whatever. But it was the certificate transparency logs that took me a few months to download all of those things. They're publicly available through a well-documented API. Most of the logs actually are very performant, so you could ask them and get quick responses. But it just turns out that downloading literally every certificate is not really well supported in tooling. Like in 2017, remember this is only a few years after CTLs became popular, but before they became required, there was an attempt at creating a tool that would download everything from a CTL, but the CTL sizes just shoosh, exploded. So I ended up having to take that and create my own version of that with basically super parallelism. I had a small 10-node cluster, and each of those clusters ran one of the downloaders that was based on this existing code. It was called Axeman. I want to say it was from Calidog. It's available on GitHub. But it was single-threaded, so I had to make it multiple-threaded. We ended up having about 100 download threads going at one time, and it still took like a couple of months to download all that data. And parsing it, download and parsing. Matching the subjects and the alternate names to the threat intelligence turned out not to be quite so easy either. Like, first of all, the alternate names have to be parsed out, and then you have to, we ingested all of this into Splunk, of course, so I wrote some fairly nice-looking SPL that could do all this for us and match against any of the names that appeared in each certificate. But some of them were still a little bit difficult, because especially when they came to wildcard names. Like you could have star.splunk.com, which would be valid for any Splunk website in the splunk.com domain, no matter how many subdomains or whatever it had. And it wasn't clear what a fair way to match wildcards were. I still won't say that I've totally solved that. What I really did was not match wildcards. The biggest problem, though, was less of a technical issue and more of a, I don't know, like a statistics issue. Some issuers were really tiny, like, or only 1 or 2 or 10 certificates in my data set. Some issuers were huge, like 1 billion. Who wants to guess for the lockpick set? Who had the 1 billion? It was Let's Encrypt. It was actually, the root CA is not called Let's Encrypt, it's the Internet Security Research Group, but yes, it was Let's Encrypt. Let's Encrypt is by far the big dog in certificate authority. It was actually interesting. One of the hypotheses from our research partners was that Let's Encrypt might turn out to be one of the worst. Let's find out if that's actually true. My first attempt at doing this kind of analysis was, let's call it the naive attempt. And I mean that in both, it's the simplest way, and also, oh, it's so cute you thought that would work. What I did was basically put them all into one big ranking. For each root and for each issuer, like I did these in 2 separate batches. This is the roots. For each root, I counted the total number of certificates that I had that rolled up to that root certificate, root CA, and then the total number of those that were present in my threat intelligence feed. And basically just made a percentage that said this is the percentage of certificates for that root CA that were involved in malicious activity. Because comparing the percentages is not necessarily the easiest thing, I computed also something called a z-score. Anybody familiar with a z-score? Maybe not. A z-score is basically the number of standard deviations away from the mean that you are. So we took all of the percentages and said, here's all the actual percentage values. What's the mean percentage, and then what's the standard deviations away from that? What's one standard deviation? Usually we use z-scores as outlier detection, and a typical value is anything with a z-score of more than 3 or less than 3, plus or minus 3 standard deviations, right? So in our case, anything with more than 3 standard deviations would have been a risky outlier because the percentage was higher, and anything with less than -3 would have been a trustier outlier. So I just ranked them. And you can kind of see, I know this is a little bit of an eye chart, so I apologize for that, but you can kind of see, here's the z-scores over here. Remember, our threshold was 3, so here there are actually 3 outliers. The first one, the Internet Security Research Group I just mentioned, they actually are one of the, they are the organization that Let's Encrypt, that runs Let's Encrypt. But there's also other ones like there's GoDaddy, and there's this one called eMudra, which I'm not really familiar with before I did this project. But look at that. The ISRG, the top one, has, what is that, a 6.3 z-score. Super bad, right? But it only has 2 total certs, and one of them was risky. GoDaddy, on the other hand, had a whole bunch of certs, and a whole bunch of them were risky. But it scored less high. Still an outlier, but it seemed like this was not a fair comparison. Same thing with the issuing CAs, except here on the issuing CAs, everything, there were a lot of outliers. This is only the top, 10, I think, and so there were even outliers below this. So there were a lot of them. But it still has the same problem. Most of these only had less than 10 certificates, with the exception of TrustOcean. TrustOcean had 10,000, most of which were bad. But still interesting data, but not a fair comparison. Because the population for each CA was they varied so widely. Here's what it looks like when you plotted on the bottom. These are all the individual root CAs. I didn't bother naming them because who could read all that? And then here on the top, this is the number of certificates that rolled up into that CA. This is root CAs. If you read this closely, which I understand you may not be able to do, this is a log scale, not a linear scale. I had to do that because at a log scale, it just looked like a straight bar and then nothing. The logarithmic scale on the y-axis actually exaggerates the y values a little bit so you could actually see them, because otherwise you really wouldn't be able to see that much. So this looks like a gentle slope, but it is actually not a gentle slope. It is a sharp drop, meaning that there are few root certificate authorities that have a lot, and there are a lot of certificate authorities that have very few certificates. I feel like that scene in The Lord of the Rings where Bilbo's at his party and being like, I like half as much of you, twice as much as, whatever it is when I say this. But there's a sharp drop. I did the same thing also for the issuing CAs, and again, logarithmic scale, this even sharper drop. So using this information about the distributions, what I decided to do would be, the fair way would be to group them into buckets. So I called them tiers, tier 1, tier 2, tier 3, tier 4. The tier 1 for the root CAs is everything that had at least 10 million or more certificates. Tier 2, a little bit smaller, 1 million to 10 million certificates. Tier 3, 100,000 to 1 million certificates. And then Tier 4 was everything else. It was really the long tail. When you do that, you are basically comparing each certificate authority to its peers in terms of the numbers of certificates, and it becomes a lot more fair. In Tier 1, it turns out there were only 13 Tier 1 root CAs, so all of them are here on the screen, and you can see that there are no real outliers. Like, there's some differences, some negative numbers all the way up to like a 2.37, but our outlier threshold we chose somewhat arbitrarily, but a normal outlier threshold is 3, meaning that all of these people, or all these roots, are roughly equal, which makes sense because these are the biggest players in the market, and they presumably have the resources to do the right thing, but also they are afraid of competition from their peers, so nobody wants to really risk being significantly worse than the others. So it made sense that there was really good quality. None of them are particularly risky or even particularly trustworthy. They all are roughly the same. When you get to Tier 2, kind of the same story. Like, the top one here is, what is that, I can't even read it, 1.9. So no outliers in the risk or trusty directions. And again, same for Tier 3. But Tier 4 is where it gets interesting. Check out some of these. Like, the top one here, again, is the Internet Security Research Group. It only had 2. I considered this noise, so even though it had a giant z-score, I kind of excluded it. The actual ones are ones that have, some significant number of certificates here. And now we get like 4 of these guys that are kind of more risky. They're risky outliers. I can't say that they're objectively risky, but they are more risky than their peers. You'll see other ones here like maybe oops. So you might see things like this one here, the top one, the eMudra Technologies. We saw that earlier. They are they claim to be like the largest SSL certificate provider in India. I take their word for it. I'm not familiar with them. If you go down, there's a similar one, eTugra, which is from Turkey. The interesting ones, I think, on here were, first of all, look at SSL.com. Like, anybody familiar with SSL.com? It's actually a legit business. It's a real business. But it is significantly more risky certificates than most of its peers. And I don't for sure know why, because it's not like I can call up the threat actors and go like, hey, Vlad, can you tell me why you chose SSL.com? But when I looked to try to explain this or come up with some theories, one of the things I did was I looked at their websites, and for SSL.com, for like, I think it was like $10 a month or something, you could request an unlimited number of 90-day certificates, and it's trusted by all the browsers, and they even have an API. Now, to me, high automation, low cost, and trusted universally sounds like a recipe for a threat actor to target them as their SSL provider. So I don't know if that's really the reason, but it seems logical. The biggest surprise on here, though, was this one here. Look at that, Google Trust Services. It actually is Google. What the heck is Google doing on the list of riskiest certificate authorities? Well, it turns out that if you run your own websites on Google Cloud or on their user-provided content pages and you want an SSL certificate, this is the default choice of providers. You can get it wherever you want, but if you just click the button or whatever you do, this is what will sign your certificate. So in that sense, it's mostly user-generated or user-provided content. Also kind of makes sense that, a threat actor just throwing up a page on Google probably with a stolen credit card information and just wanting it to all be to work with the minimum level of effort, clicking the button and letting the defaults go through, seems like it's likely. In Tier 4, we didn't really have any particularly trusted. We had a few not trusted, but no particularly trusted things. And we did the same thing, kind of broke them up into tiers for issuing CAs. We had different levels. So Tier 1, the largest issuers were 100,000 or more, all the way down to Tier 1, which was less than 1,000. In Tier 1, we did have a couple of outliers. You can see we had GoDaddy. I wasn't sure why GoDaddy showed up here, but the closest I could come was maybe it's because, they're not particularly cheap or particularly automatable or anything, but maybe because they are also one of the largest hosting providers in the world, it made sense that, again, threat actors that might be using GoDaddy would use GoDaddy's certificate authority. I could kind of see that. And a similar thing here with Zero SSL, kind of highly automatable, a little bit less expensive than typical, so maybe, again, that's one of the threat actors there. Maybe that's why they're using it. Again, no really trusty issuers on Tier 1. Tier 2 risky issuers, really just the one, TrustOcean encryption. TrustOcean is a Chinese certificate authority. I don't really know what to make of it. When I created this presentation, their website was not responding at all. And apparently, according to Domain Tools, hadn't responded for some time. They have some GitHub repos out there, but they haven't been updated since 2019. So my assumption was that they went out of business before I could check up on their procedures and see why they might be a risky issuer. However, I just checked this afternoon while I was prepping for this talk, and I see that their website now does respond, but it's not the same domain as before. It seems like maybe they got acquired or somebody took over. I don't know exactly what happened, but the GitHub repos now, their website actually points to some new domain, and that domain is working. So I'm not sure what to say about TrustOcean. I can't even say that I think they went out of business anymore. Now I can just do I don't know. But I wasn't able to come up with a theory because I just didn't have enough information. No particularly trusty outliers on Tier 2. For Tier 3, we had a bunch of outliers, some of which you can see here. TrustSafe. There's that eMudra Technologies again. Another DigiCert Rapid SSL. Again, I think Rapid SSL, high automation, perhaps. There's another eMudra down here. Both of their issuers being on here probably goes a little bit to explain why we saw them earlier in the root CAs. So there's all kinds of stuff. Again, though, on Tier 3, no trusty outliers. We're starting to see a pattern. Nobody's particularly better than their peers, but there are a few that are notably worse than their peers. When it comes to Tier 4, though, there's just literally so much. Like around 72,000 of the 78,000 issuers actually came in Tier 4. And there's just so much noise in there that even though these z-score numbers look huge, like the total numbers are really small. So we just ended up considering all these to be noise, and we excluded any of the tier 4 issuers from our calculations. So, conclusion, who's still awake? All right, mission accomplished. Sum it all up. I looked at all these things at both the issuer's CA and the root CA level, and we identified 4 outlier CAs in the risky direction and 10 outlier CAs, issuing CAs in the risky direction. I'm not saying that all of those were inherently evil and bad and you should never trust their certificates. Blocking certificate authorities, like people are like, okay, great, I got a list of risky CAs, I'm just going to block them and then I will have no risk anymore. Blocking them is probably not really warranted, even though that might be our first thought. It's because we're not likely to see most of those certificates because they typically are not in the highest levels. They're the lower echelons for the roots. And there's no way to block issuing CAs. Like you can't just remove an issuing CA from your cache because they're not in the trusted cache anyway. What you can do, though, if you're not already doing it, is use a tool like maybe Zeek or something similar that will observe all the TLS transactions and log the details of the certificates. Because remember, the certificates can't be encrypted yet because exchange of certificates is part of setting up the encryption. So they're all in plain text, binary, but plain. And so you can actually log them, and Zeek will do this pretty much out of the box, and it will give you a lot of details, including the certificate authorities. And you can use those certificate authority data to do like risk-based alerting or data enrichment for incident response or threat hunting or something like that. If only you had the data of the risk rankings for all of the certificate authorities. Some things that we didn't get around to that I would have liked to have tried, and maybe if someone wants to take this to the next level, they can also try a little bit longer certificate history, longer threat intel history. We could have tracked variations over time rather than as a snapshot, which would have given us a better view over who was actually doing worse or better. So that one might have been nice. I did mention that we could have done better on the name matching. The biggest one, though, is I really tried hard to get our threat intel partners to do this work again, like on a regular basis, because I did it as a snapshot in time, but it gets stale. So if you're going to use it for data enrichment or risk-based alerting or something, you need fresh data. Weirdly, none of the threat intel providers seemed that interested. Like a couple of them were like, that's really cool. I have wished for this, but we couldn't make a business case out of it. So, you know, if this sounds interesting to you, maybe talk to your threat intel providers and ask them for it. Some next steps for you. First of all, remember I said that ranking data, if only you had it, you could do something with it. Well, we actually made it available. It is in a GitHub repo here at this highlighted URL here, and it actually is the top 10,000 domains in issuers out of 72,000. You might be like, why didn't you give me all the rest of them? But actually, that's really all you need because it fell off into the really long tail after that. So 10,000 has pretty much everything you're going to need, and all of the root CAs are ranked in there. So you could download those. They're a few months old by now. They were fresh in May, but still useful. So you could actually go home, start logging the TLS data, pull down the risk rankings, and then maybe try out some threat hunting use data enrichment. Like, hey, are any of my users going to sites that are signed by any of these issuers or root CAs? Maybe that would not be useful enough information when, to make an alert or something like that. But if you have a whole pile of data that you're trying to winnow through, maybe that will be one useful data enrichment. And again, like longer term, it would be great if we could all beg our CTI vendors to provide those risk rankings on a regular basis so we could make sure that they stay useful. And with that, I guess I have a couple minutes for questions, if there are any, if anybody's still awake. I had some. I think I saw your hand first, sir. Oh, so the question is, did the threat intelligence, did they differentiate between somebody who created a website specifically for evil versus somebody who compromised an existing website and used it for evil, right? No. No. None of that was in the data. I think just because the CTI providers probably don't know the answer. Other questions? Yes. Yeah, so this question was, if you're a website owner, is there a way for you to prevent your legitimate users from falling for like impersonation websites with signed certificates that look like you but are not actually you? Again, no, not that I'm aware of. It would be nice though, wouldn't it? But that would solve so many problems. Okay. Well, thank you very much. I hope you've enjoyed it, and go download my risk rankings.